So honestly, the other thing about assignment 4 being big is that there's all really good stuff in there. And the thing that makes me sad is that the information that's included in this week's lectures and assignment 4 aren't really very widely disseminated, which is kind of why I was like, I've got to cram this all in. If you understand the things that we talk about this week, it's already going to put you way ahead of a lot of people in the software world, particularly the stuff we're going to be talking about today, because it's exception handling, and people generally don't understand how this stuff works. It's very complicated. I shouldn't say complicated, because as you see, it'll be straightforward to understand, but it's very advanced, I guess is what I'm looking for here. So yeah, we have higher level languages using exception handling. Who's used exception handling in a language? I expect that probably most of you have. Yeah, that's what I would expect. So we're going to talk about how this works. The whole idea behind exception handling is that I have one part of my program that knows how to detect an issue, but it doesn't know what to do about it. I try to connect to a remote server, and the server doesn't exist. Do I reboot the computer? Do I stop the program? Do I ask the user for more input? I don't know. It depends on in what context I'm making that connection. So then you have another part of the program that knows how to deal with the situation, but it doesn't know how to detect it. If those two pieces of code were in the same place, it would just detect and handle the problem. But we have many situations where we have generalized libraries and so forth, where the code that detects the issue isn't the same as the code that resolves the issue. So exception handling is one way of handling these situations. There's several other ones as well, but the idea is that I will throw something called an exception, which is a special value. It has a type, and the type indicates the general category of issue that occurred, and the values inside give specific details. So this is the concept of exception handling. And we're all familiar with this. The code that knows how to handle it can catch the exception. And the neat thing about this is that does not have to be in the same function. It can span multiple function invocations. I can have a piece of code and call it from one place, and when it throws the exception, that code handles it. I call it from another place, and it throws an exception, and that code handles it. So it's a very powerful mechanism for propagating errors. Now, the way that Java does it is with try-catch, and this is a very simple example that I tend to use in my Java track anyway, so if you've already taken that track, I apologize, and if you do in the future, you'll see this again. So we have code here, just some main function load config, and then inside we read some input, compute a value based on that input, print out the result. Very straightforward, and we have a try-catch block in here, because if compute value gets something it can't handle, then it will throw an illegal argument exception. And what will happen is it'll transfer execution straight to the catch block. So we skip over everything else. And so instantly you can sort of see that this is kind of like two things we already understand. It's like goto, and it's like returning from a function, because we are coming from another function and we're jumping to a specific location. So that is going to become important today. If we have other exceptions, then they're not handled if they're not within a try block. So in here you can see if load config were to encounter some invalid input on the command line or something like that, if it throws, well, our program isn't intending to handle it. And that's just by virtue of where we've put the try-catch blocks. If we wanted to handle it, we'd put it inside of a try block. So like I say here, if this code throws, the code inside the try block, if that throws, then I want to handle the exception if it is one of the types that is listed in the catch blocks. Okay? And so that also sort of gives us an indication about how to think about this, because clearly when we enter a try block, we need to pay more attention. Something important could happen, so when we're inside the try block, it's going to be more important than when we're outside the try block, as far as exception handling is concerned. Okay, so here's the code for compute value. You can see that we say x has to be at least 3 because we want to take the square root of x minus 3. It's a very complicated function. And so if x is 2, for example, we won't be able to compute the result because math.square-root doesn't generate complex numbers. And so we just throw an exception instead. And yes, the function can complete in two ways now. We can either return to the immediate caller, which we already understand because we use stacks. We could put it, if we were translating this directly into C code, we could just, or I should say assembly code, we could put that into EAX and it would go back. That'd be no problem. But we could also terminate abnormally. This computation could be terminated by throwing an exception. And it's weird because we just sort of drop everything that we're doing and we leave. So if there's more code, it doesn't matter if there's 100 lines of code or 2 lines of code. We're just like, okay, that's it. I'm done. I give up. I quit. And so it will jump to the nearest enclosing try-catch block. And when I say enclosing, of course, that's the sequence of calls. Just like I was saying, if I call it from over here and it throws, then I go there. If I am somewhere else and it throws, then I go back to there. So it's kind of interesting that way, that it has to know where the caller is from. So you can see that it has a strong resemblance to subroutines. You can use exceptions in a single function. This is a very uncommon way to use exception handling. But I find that it's very useful when you're trying to process command line arguments in a language that doesn't have gotos, like Java. Goto, I believe, is a reserved keyword, but it's not in here. Who thinks that gotos are universally evil? Who was taught that like early on programming? Wow, okay, so things have changed. A few people? Yeah, so what you'll find is that gotos are generally a bad idea unless you know how to use them in a restrained way. And you may notice that in some of the code that I give you, that gotos are fantastic in a language like C, where you don't have exception handling and you need to jump out of a function when you can no longer do your work. So sometimes those things are useful. That's an aside. But anyway, so you can see here I'm trying to process command line arguments, and if I have a situation where I see an argument and it's supposed to be accompanied by a value and it doesn't have that value, then I'll throw an exception and skip over everything else and just say, hey, I ran into a problem, print usage, and then get out. Okay? So that's like one of the few places where I use exception handling within the same function in Java. Okay. Now that's an obvious simple way of using it. The more common way is when you have multiple functions involved. So here would be an example where we have load page. This might be for your web crawler for Java Track Lab 6. And so you pass it in a URL, and what you want to do is send the HTTP request and get back the contents of the web page. So we try to establish a connection using a socket. You can see in the second function, send HTTP request. And if the server is not there or there's no server listening on the specific port, so port 80 or whatever port that you need to connect to, then the socket constructor could throw an exception, and send HTTP request doesn't know how to handle it. So it'll just let it propagate out. I should actually have something like throws IO exception if I'm going to be really accurate as far as the Java code. But anyway, it'll propagate out, and the caller will be able to handle that error in whatever way it sees fit. So we're abnormally terminating the send HTTP request function. So you can see that this is a bit of a challenge to implement, especially if you want it to be efficient, because there's actually a really straightforward way to implement it that is kind of slow. And we'll look at the slow way. You'll get to implement a central part of the slow way in assignment 4, which is probably one of the most challenging parts of assignment 4. And then there's a really fast way that involves things that C basically can't do at all. And so you don't have to implement that, but it's really interesting to understand. So anyway, like I said, the exception can stay within the function. It can propagate across multiple function calls. And the catch handler to go to depends on how did I get to the code that threw. So you can see that I have to know what try blocks I'm entering as I enter them so that I can then handle the exception properly. I can jump back to the appropriate try catch block. And of course, we'd like it to be fast. This is where we say, yeah, and I'd also like to have a pony. But we'd like to have no overhead in our program in the normal case. We call them exceptions, and so if it's going to be slow, I'd rather it be slow in the exceptional case rather than in the normal case. Okay? So like I say, the assumption is that exceptions aren't going to be thrown very often. There was a phase when Java was pretty young, like Java 1.1, Java 1.2, where people got really excited about throwing exceptions willy-nilly, and I think thankfully people have grown out of that. But people noticed that it was faster, for example, to just iterate over the elements of an array and then catch the illegal, or I should say, what is it, array index out of bounds exception when I pass the end of the array, than it was to write a stinking for loop and iterate over the elements in a for loop. And I'm like, okay, this is really bad that people are using exceptions this way. So thankfully, we've kind of grown out of that. So yeah, 2 important points in program execution. What do you guys think those are? Should be pretty obvious. I mean, one of them is really obvious. When I throw, something needs to happen, and I need to figure out, okay, what do I do when I throw? But there's another important point in our program execution that we need to think about as well. And I kind of pointed it out early on when I said try means I care about exceptions in this code. If it's outside of a try, I don't care. That's somebody else's problem. But if it's inside the try, I care if an exception is thrown. So these are basically the two important situations we need to think about. Okay, so when I enter a try block, I may need to think about what's going on, because if an exception is thrown, this try block will have an effect on how to handle that exception. So like I say here, we may need to do some kind of bookkeeping so that we know where to go back to. The other situation is when the exception is actually thrown, because then I need to rely on whatever bookkeeping information I have to know how to get to the appropriate error handler. Okay, so like I say here, we need to have the information from the most recent try, and then if that try doesn't handle it, then maybe the one enclosing that, and maybe the one enclosing that, and so forth. And like I say here, it does frequently cover multiple stack frames. Now let's say that we have a situation where the exception is entirely within a single function. Okay, this is like our error checking function, our command line argument parsing function initially. Okay? We try something, if it failed, we throw an exception, and then we just catch it in the same function. In general, if you do this kind of thing, you probably aren't using exceptions correctly. So this is a very, very uncommon case. But if we have a situation where it is entirely inside the function, we could just use a goto. Right? We just say, oh, instead of saying throw new exception, I'll store my exception somewhere, and then just jump to the right place to handle it. I can do that. It's within the same function. And like I say, we do need a way of passing that exception object. And so what most languages that have exception handling actually assume is that I'm only ever going to have one exception in flight at any given time. Okay? Which is kind of an okay assumption to make, because you do have the rare situation, like in C++, if the ship is really going down fast, you could have an exception being propagated, somebody tries to throw an exception, and when it tries to throw that exception, the runtime runs out of memory, and so that exception is replaced with a bad alloc or something like that. So the actual exception gets masked. So you have a few situations that can occur where this assumption can cause us trouble. But in general, we'll assume that there's only one exception in flight when we're actually throwing something. So like I say here, we can have a global variable, we can have some memory area, and we can store our exception there. And that is, in fact, exactly what C++ does. It always guarantees that there will be at least enough space for bad alloc so that it can say, I couldn't allocate memory, and anything larger than that, it may have to do something more fancy. So here's one possible translation. Notice, if failed, we've just taken our throw new exception code and we turned it into something that sets the exception in flight. We jump to the catch exception part. If we finish the try successfully, we jump over the catch, and our catch block just does whatever it's supposed to do. I don't know, I don't care. Okay? Very straightforward, naive translation. Okay? The problem is, we can't use this technique if we have exceptions spanning multiple functions. We don't have any way of go-toing from one function's body into another function. Let's say that we have this code. So f, g, and h, we call f, and it goes and calls g, and if g complains, then it will catch the exception. G calls h, and h is the thing that if it gets a value that's less than 5, it's going to throw an exception. Okay. I just realized that all of these functions take and return ints, and we're using square root on it, so I don't know that that makes a lot of sense, but just roll with it. So, but anyway, you can see now that we have a problem that we can't hard code a jump from H to F. That'd be really bad. What if we had some other code that called G and it wanted to handle the exception? Well, then H jumping back to F would be horrible. We would end up in a function that we have no idea why we ended up there. Okay? So what we need to do is have a way of recording where to jump dynamically. And then once we have that, we can use that information to go back to that location, even if it spans multiple function calls. Okay? So this is what we need to build. Who's heard of set jump and long jump? Anybody here? Okay, well, you guys get to not only hear about them, but learn how to implement them this week. So there's these two functions in the C standard library which blow your mind at first until you understand them, and then you just get really scared when you have to use them because you don't know if everything will work exactly right. You have set jump. Notice it takes this jump buffer thing, jump buff, that's an array, that's all it actually is. And what set jump does is it records the execution state at the point that set jump was called. Okay? And like I say here, the recorded information is the callee save registers. Because you're entering a function, you expect that function to follow cdecl. So set jump has to follow cdecl. It saves the callee save registers. It saves the stack pointer. It saves the caller return address, which is kind of an unusual thing. Those all go into the jump buffer. And set jump is defined to always return 0. Okay? So that's set jump. Long jump takes a jump buffer as well and a value that it needs to return. Okay? Except that you'll notice that long jump is defined to return void. What long jump does is it restores the execution state from that jump buffer back into everything that set jump took it from. So it restores the stack pointer. What is that going to do? Change what frame is currently on the stack. It restores the callee save registers. It does all that stuff. And then it sets up the return value. Yeah, like I say, the ESP is restored from the environment, so that discards any intervening stack frames. And the stack is basically set up as if set jump was the function being called. Okay. So like you see here, the caller return address is put back on the stack that set jump saw. Then long jump returns a non-zero value. It will either be val, or if the caller said that val is 0, long jump is defined to return 1. Okay, so this is what long jump does. So it's really weird. Set jump is a function that you call at least once. Because you call it, and it looks like it returns once. It can also look like it returns a second time, or a third time. Depends on how many times you call long jump. Long jump is a function that you call, and it never appears to return. Because when you call long jump, it's like a wormhole. It goes back to where set jump was called. And the only way that you can tell that you're returning from set jump as opposed to returning from long jump is that set jump will return a 0 value if it was really an invocation of set jump. Long jump will make set jump look like it returned a non-zero value. So that's how you tell the difference. Okay? Non-local goto, or inter-procedure goto. That's what this thing is known as. And yes, it's a real thing, and yes, it's actually used in software you probably use every day, which is pretty crazy. Okay, so we can definitely implement the previous example using set jump and long jump. Remember again, the important points are when I enter the try block and when I throw an exception. So what do I do when I enter the try block? I call set jump. And set jump stores the environment and returns 0, so I know that I haven't actually seen an exception yet, so I can go ahead and return G, I propagate into G, and then I enter H, and if a problem occurs in H, well, instead of throwing an exception, I will just long jump to wherever the jump buffer says I'm supposed to go. And I'll say, this is a non-zero return value because guess what? There's a problem now. So when I call long jump, I end up coming back out at set jump again, and this time the value is non-zero, so I know an exception occurred, so I can just return -1, just as the code on the left has. Okay, questions? Who's completely confused? I think this is totally awesome. It's like one of the coolest functions. Okay, so yeah, like I say here, when we enter the try block, we record the execution state just in case, and if an exception is thrown, then we use long jump to go back to where the enclosing try is. And the nice thing is that this is super fast, because we basically completely chuck H's and G's stack frames. We just throw them out. We don't even worry about it. We just reset the stack pointer to where it was before. We reset the instruction pointer to where it was before. We just pretend G and H never happened. So we basically abort that computation exactly as you would expect it should be. And then, yeah, you see the return value of set jump basically indicating whether or not an exception occurs. Okay, any questions? There's all kinds of ways that this can go completely haywire, which is why if you read the C standard about how set jump and long jump work, it gives you all kinds of warnings about what you're allowed to do and what you're not allowed to do. This is an acceptable usage. There are many unacceptable usages of set jump. Okay, so F5, let's say we pass in F5. We get an exception because we get G of 15 and then H of 0, and that's definitely less than 5, so we get an exception. So just to go through this, F5 calls set jump the first time. So we enter F with the argument 5, and it calls set jump and gets 0. And so inside set jump, you can look at what the stack frame would look like. We have the one argument to set jump. It's that jump buffer. So that's a pointer. We have that on the stack. We have the return address to inside the comparison. That's important. And then we have the stored base pointer of f of 5, presuming that set jump saves the base pointer. It turns out that you don't actually have to. But in fact, when you implement it, you may find that it's easier not to store the base pointer. I'll leave it up to you what you decide to do. Anyway, but you can see that the caller's base pointer and the return address are on there. And so what does set jump do? Well, it saves callee save registers, saves the stack pointer, it saves that return address. The return address is inside that comparison. Okay, so those all come off the stack and out of the registers and go into the jump buffer. So now the environment holds everything that's needed for long jump to pretend like it's coming back out where set jump is. Okay, so set jump returns 0, and F5 calls G of 3 times 5, which is 15. And so now we have the frame for G of 15. So you see we have one argument for G. That's on there, the return address to F5. Now notice, this is a different return address. Now it's the one right before the return from F. So we're outside of the comparison. We're in the return now. And G does its thing. And yeah, like I say here, the stack frame from set jump is gone now. But there's another important detail, which you'll notice that the caller of set jump still has their frame on the stack. And that's one of the requirements of set jump, is that when you long jump back to a function, that function must still be in execution. If you call set jump inside of a function and then that function returns, then when you long jump back to it, you'll be jumping into an invalid frame, and boom, your program will explode. Okay, so you have to make sure that you always long jump back into a function that's actually running, or that has a frame on the stack still. Okay, so let's see, now we're in G15. G15 calls H of 15 minus X, so we have this now. We have G's frame and H's frame, and you can see 15 minus X is 0. That's what H sees. It has a return address to return H of 15 minus X, and so forth. Okay, so that's what we have now, except that H can't handle this, so it needs to abort the computation. So it throws an exception, and what it does is it calls long jump, which basically sets everything back up, restores the registers, restores the, what else does it restore? The stack pointer. It restores the return address on the stack so that when long jump returns, it goes back to where it was called, or where set jump was called. Okay. So like I say here, it restores the execution state back to the execution and now. And more specifically, it goes back to exactly after this call set jump function instruction. So that we're still inside the comparison now, except that this time EAX will contain non-zero, so it'll see that the equals 0 fails, and it'll say, oh, I have an exception. And it will go ahead and deal with that as if it invoked the catch. Okay, does that make sense? It's pretty neat. Oh yeah, hey, look, Squirtle. That's the long square root function. So I guess I did handle the fact that it's ints. Okay, for whatever that's worth. Let's see. So yeah, H calls long jump, ESP and caller EIP and EBP are restored from the environment. So you can see that basically what we do, this is where we get that whole notion of we just chop down the stack, even though we're kind of chopping up the stack, but you can pretend it's all upside down. So or stand on your head if you're good at that. So anyway, we restore the ESP from the environment so that automatically eliminates all the intervening stack frames. We restore the return address and the caller's EBP. If we happen to store it on the stack, we go ahead and do that there. Okay, so you can see that basically long jump goes in and completely mangles the stack, but it puts it back to the way that set jump had it. Okay. And so like I say here, when long jump returns, as far as F knows, it came back from set jump again. Has no idea. Okay, so set jump and long jump can be two completely different functions, but because long jump manipulates the stack, following cdecl, all of that kind of stuff, when it returns, it looks like it came back from set jump again. Okay, so that's basically the idea here. So like I say, set jump and long jump are crazy beasts. I didn't even really, like the first couple years that I taught CS24, they were too magical for me to give them to you as an assignment. But now that I understand them and see that they're actually not that terribly complicated, I have you implement them. And I think that you'll find it a fun brain teaser. It really is all about cdecl and making sure you understand the calling convention and manipulate things following the calling convention so that you can just go back to where you came from appropriately and fake it like a wormhole. Okay, so like I said, there's no C mechanism for doing these things, so we have to implement set jump and long jump in assembly language. And this implementation is very platform specific because obviously it depends on what registers I need to save. Is it callee save, caller save, how many registers do I want to preserve, and so forth. Okay, these are some examples. So Linux on IA32 uses 8 D words. Okay, so it has 8 spaces for storing things. OS 10 uses 18 D words. So it's going to be saving things like SIMD, floating point registers. I mean, you saw that we had floating point, or we could have floating point computations going on. We need to save the floating point registers as well. On PowerPC, which nobody really runs a OS 10 on a PowerPC anymore. That was long, long ago. That uses 192 D words for its jump buffer. So since the specification is ambiguous, you end up with implementations that are very platform specific and OS specific. Okay? Yours will definitely be much more on the smaller end of the scale because it turned out to be very straightforward. Okay, so like I said, you really just need to understand cdecl pretty well. So in set jump, you just need to know how to save the caller's execution state. Okay, where did the caller call you from? Well, remember, when I call, the return address gets pushed onto the stack. And so ESP, basically, when I come into the function, ESP is pointing to the return address. I can just squirrel that away somewhere. Callee save registers. The caller expects that those are going to be the same when the function returns, so you have to make sure to save those. And then in long jump, you basically just have to set things back up the way that set jump saw them. So it's pretty straightforward. Okay. Let me see what time it is because I want to. Okay, 11:34. Yeah. So with multiple catch blocks, you can see that this is certainly a possible way that you could use exceptions as well, where I have multiple exception types that I could catch. And it's really not that much more difficult to add this to our set jump, long jump capability, because remember, we have this int value that we can return. We could just assign each exception object or exception type its own integer value representing that type. And that way, on the set jump side, we can just do a switch statement or something saying, well, if it's 0, if the result from set jump is 0, do your normal thing. Otherwise, you can have an entry for each one of these catch blocks. So I have a little example of that. This is also a valid usage of set jump. There's a lot of stuff that you can really go haywire with set jump and long jump because you can imagine local variables, if they're stored on the stack or if they're stored in caller save registers, things like that, then the use of set jump can really mess all that stuff up. And one of the things about what the standard says about using set jump and long jump is that if you use them incorrectly, you may see local variable values change. You may see other things change really wildly. You may see variables restored to, so if you call set jump and then later on change local variables, and then you long jump back, you may see those local variables roll back to the state that they were in before. There's all kinds of little nuances, so you have to use set jump in very limited scenarios. Like we have here. I just have it as the argument to a switch statement. Okay, so that's pretty straightforward. Now, the other thing that you need to think about this with exception handling is that there is a flaw with this. We basically have only had one try block, but you can nest try blocks in your execution as well. So I can have one function that says try, and it calls another function that says try, and if they both happen to want to catch the same exception, and the exception is thrown, I need to go to the second function, not the first function. So I need to be aware of this nesting of try-catch blocks. Okay? And we only have one jump buffer in our example. So the solution is really easy. You just need to have a stack of these things. Every time you enter a try block, you generate another jump buffer and push it on the stack. When you exit a try block, you pop it off. If you catch an exception, then you pop off the thing because you used it to handle the exception. Okay, so it becomes very straightforward to implement nested exception handling with this mechanism. Okay, I just want to point this out. The reason why is because that's exactly what you have on assignment 4. I just use that as an example to show how you can build exception handling into the C programming language. It is slow, but it totally works. Okay, so the program enters a try block. You call set jump. If it returns 0, you're good. You push the jump buffer onto the try stack. And it's kind of interesting. I actually got bit by this. I tried creating a primitive that would, or a function that I could call set jump from inside. And then, that function would basically return the set jump result, and then, life would go merrily on. But there's a problem with that. And I'm not going to explain what the problem is. It's something for you to think about. But if you understand CDECL and you understand stack frames, it should be relatively straightforward to sort out why you can't have a helper function call set jump for you. You have to call set jump yourself. Okay. Now, like I say, when the program exits the try block without any exceptions, you're done. You're leaving the try block, so you pop your try block's jump buffer off of that stack. And like I say, you can do this in a helper function. That's okay. When you throw an exception, you have some helper function that basically calls long jump for you with the exception ID. And like I say, it pops the topmost jump buffer off and then uses that jump buffer to go back to the enclosing try block to see if it can handle it. Now you may have a situation where inside of that try catch, it doesn't handle that exception. Well, that's okay. What you do is you propagate out of that try block. So again, you pop another jump buffer off and you long jump to that one. So you just keep propagating through all the try blocks that you might be nested within. Okay. So the homework assignment gives a lot more detail about how this works. That's, I'm sure, more than a few of the 11 pages in the assignment write-up. So it sort of shows the translation that you can use to build this exception handling mechanism into C. Okay? All right. Any questions about this? Some interesting notes about it. You'll see here that this is fast when we propagate exceptions. It's slow through the tries. So right now we're incurring a penalty every time we enter a try block, even if we never throw any exceptions. I want you to think about that. Okay, we call this stack cutting. And like I say here, we chop down the stack. I like these violent metaphors for programming. So yeah, the intervening stack frames are basically eliminated. And this is good and bad. It's fast, like I was saying. It's very fast for exception propagation. But what if we have pointers to memory that we allocated? Junk like that on the stack. And we just throw away those stack frames. We lose those pointers to the memory we allocated. So if we need to do cleanup, then we have to think about what is it that we're eliminating on the stack. If we have some way of recording the resources that we allocate along the way, then you can see that as we propagate exceptions out, we can easily clean those things up. I shouldn't say easily, it becomes straightforward, but you can see that it starts to get more and more complicated because I have to make sure I clean up after myself when I leave functions. And this is where garbage collection is a real benefit, because if you have garbage collection, then you don't care. Because if you have pointers on the stack, well, or I should say references, if we're talking about language with references, when we chop down the stack, we are able to just let the garbage collector go through and realize that those things are now unreachable, and it will reclaim them for us. So GC helps us a lot with this stack cutting mechanism. Unfortunately, so the exception handling mechanism that I give you guys in the assignment can't handle this. And so if you malloc inside of a function and then it throws, you just lost that memory. You're sad. Okay. So that's stack cutting. And like I was saying, stack cutting is fast in the exceptional case, but it's slow in the normal case. And so it's not particularly desirable. And because of that, we have another technique that is actually the one that is mostly used, and it's called stack unwinding. It's used by the Java virtual machine. C++ generally uses it. And if you dump the binaries from a C++ program, you will see this mechanism implemented in the binary. So it's pretty cool. And stack frames are cleaned up individually, which makes it very easy to handle this resource deallocation problem. Okay, like I say here, when we enter a try, we care because we may need to handle an exception that was generated in that code. And we also care about when an exception is actually thrown. So these are the two cases we need to care about. Remember that there's usually a trade-off between time and space. And so in this situation, what the compiler does to support stack unwinding is it actually generates an exception table for every function in your program. Okay? And then all the exception propagation is actually driven from the exception tables. Okay. So exception tables have a small amount of information stored in them. They have a starting instruction pointer, an ending instruction pointer. Those tell the extent of the try block that we care about. You have the exception that you care about from that try block. So if you say malformed URL exception is one of the ones I catch, well then that would be recorded in the exception table. And then the handler's address for that exception type is also recorded in the exception table. So we have 4 values in each row. And so like I said, if you have this code load page and you handle a couple of different exceptions, then the compiler might generate an exception table like this. It says, this is where the try block starts, this is where the try block ends, this is the exception I care about, and this is where to jump to. Okay, so the try block, you can see that these two, since they're both part of the same try block, from EIP and to EIP are the same. The exception is different, and the handler addresses are different. So whatever they might be, those are all made-up values. What might be easier if you're really curious about this is to not look at C++'s exception tables, but look at Java's exception tables. There's a Java P program you can use to dump class files. And I believe that you can use that to look at the exception tables for code as well, if you're really curious to see this all in action. Okay. So when you have an exception thrown by a function, you have basically 2 things you need to care about. What is the exception being thrown? Because that tells me what lines to look at. And it also needs to know what is the instruction pointer of the throwing address so that I can figure out, is this inside of a try-catch block or not? Okay. And remember that this is handled on a per function basis because now we're unwinding the stack. We're taking each frame individually. So when an exception is thrown inside of a function, I look at that function's exception table. And I look in there and I say, did this exception occur within any of the lines? Do any of the lines match? If they do, dispatch to the handler EIP. Otherwise, this function needs to be unrolled, or I should say unwound from the stack, and I need to go to the calling function. Okay, so I can say here, try to find a row where the program counter matches and the exception type matches, and if I find it, then dispatch. Otherwise, clean up the stuff on the stack and go to the parent frame. That's basically what we do when we unwind one function from the stack in this exception handling. So here's even more complicated. So f of x, notice that f can catch a or b. It calls g. G can catch b or c. This is really all we've changed, is that now we have multiple exceptions. And h can throw a or b, but it doesn't catch anything. We have these 3 exception tables that might be generated. So again, notice that f's from and to EIPs are the same because it only has one try block. G has same from and to EIPs because it only has one try block. And H is super simple because it doesn't have any tries. So it doesn't have an exception table at all, really. I mean, its table is empty. Okay? So we call f minus 9. What happens? Okay, well, we get g of minus 27. We come back down here. 8 minus 27 is what? 35. And that's above 23. So we know that a is going to be thrown. It's going to propagate through g. It's going to end up in f because g doesn't catch a. It catches b and c. Okay. So yeah, g minus 27, h of 35. This is the cool thing about stack unwinding. Remember how stack cutting would have worked. I would enter the try in F, and I would be like, okay, I got to generate a jump buffer. Did set jump return the right thing? Store that onto the jump buffer stack. All of that malarkey. Okay? I didn't have any cost. Now, I just started executing code. Same thing with G. I'd go into G, and I generate another jump buffer. Oh, did set jump return the right thing? So you can see that the normal case here is no cost. Exception handling so far has not incurred any cost except for the extra space for the exception tables for these functions. But we do know that h of 35 is going to throw. So what happens is h of 35 throws a, and the exception tables are used to drive that process of propagating the exception. And so you can see that it's not just the exception table, it's also the current contents of the stack. The current contents of the stack are what steer us to who called whom. And so that's the other part of this picture, of course, which we don't really mention here. So h of 35 throws a. I concocted an EIP for that. We look at the exception table and we're like, nothing matches because the table's empty. Okay. So since nothing matches, I clean up whatever local state that h has. So if there are, if I'm in a language with destructors like C++, I invoke the appropriate destructors, I clean up, and then I have to go and unwind the local stack frame from the stack and go back to the caller. Okay. So now h no longer exists. I've cleaned it up. So now we're in G, and we sort of think of G as if G threw the exception. But it threw the exception where h was called. And that's inside of a try block. So hey, now we get to actually start looking at stuff for our exception table. Okay, so EIP is 2123. That definitely falls within our from and to address ranges because we don't really do anything else outside of the try. So, but if we look at it, you say, oh, okay, we throw A, but we don't have B, or we don't have A in our exception table. We only have B and C. So I'm going to propagate out of this one as well. So again, G stack frame is unwound. If I have any destructors to call, I call the destructors. If I have any local state, it gets cleaned up. And G is unwound off of the stack. Okay. So then we finally end up back in F of minus 9. And again, we think of it as the exception propagated out of G. So we say that is where the exception came from. And the EIP is as specified here. And we check the exception table for F and we say, aha, now we have a matching line because that first line says try, and we're inside the try. It says if A is thrown and A was thrown, let's go to that handler. Okay? And so we dispatch to that appropriate handler. Notice return minus 5 is what that handler says to do. And we're done. We've handled the exception. Okay? You'll notice if we never reach a point where we have a particular entry in our table that matches and we get all the way up to main and we propagate out of main, we have nowhere to go. Our program terminates. That's basically why the program terminates, because we're taking frames off the stack until we run out of frames. Our program isn't running anymore. Okay? Any questions about this? This you do not have to implement. I have wanted so badly to implement this, but I never have time to sit down and figure it all out. Plus, it gets crazy complicated when you start looking into variable lifetimes and scoping and calling destructors in the appropriate order and all of that. So it's just pretty crazy. So you see that, just to summarize, this is something I've already said, but stack cutting is optimized for the exception propagation phase. It is not optimized for the normal phase. We have to do work every time we enter a try block. And in fact, we have to do work when we leave the try block because we have to pop those jump buffers off of our try stack if we didn't actually have an exception. Okay? But when we do have an exception, it's super fast. We jump straight to the appropriate place to handle that. So you can see that it goes very fast. We can't clean anything up, so we just kind of assume we don't have to. So this is not ideal. If we have a lot of exception handling in our program, you can see that the stack cutting approach is going to get extremely expensive for our program. Even if my program never throws a single exception ever, I have a big, heavy cost. Stack unwinding is different, though. This optimizes for the normal case as opposed to the exceptional case. I don't have any bookkeeping to generate when I enter a try block because the compiler already generated that bookkeeping at compile time. It's saved in the binary so that the runtime can refer to it when an exception is actually propagated. But you can see that exception propagation is slower now. I don't just chop down the stack. I take each frame individually and I handle it. So that's much slower for the exceptional case. Okay. So if I have a situation you can see where, for example, I throw exceptions frequently, that's why this gets really expensive. Because I'm handling each frame individually. So that's why exceptions aren't an ideal way of doing your flow control. Okay, so like I say here, the typical exception is that exception handling is an uncommon occurrence. We call it an exception for a reason. We don't call it the fancy pants jump, which you could if you wanted to have that be the normal case. Okay. So so we have various other things. And Java is interesting because even though we throw away references, okay, cool, we throw away references, we know the garbage collector will run all of that. We still have other things that need to be released. Like if I'm inside of a synchronized block or multiple synchronized blocks, those monitors are going to have to be released when I propagate out of that code. So those things need to be cleaned up even though I have garbage collection. So that's why stack unwinding works better for that. Okay. There's other things as well. If you're really curious about this, I can point you to various documents about how exception handling works, but I have to warn you that they are very few and far between on the internet. It took me several months to suss out all these details so that I could share them with you all. But like I said, it is a very powerful mechanism, and I wanted to make sure that you guys got exposure to it. Because if anybody ever asks you, well, how the hell do exceptions work? Well, you've seen it. You may not remember all the details, but they should come back pretty quick. So any questions? All right, so let me just give you a little heads up because it's almost 5:02, so you're almost out of here. But Monday we're going to start a completely different topic. We're going to start talking about hardware again because we're going to start getting into caching. And Wednesday, I believe, is going to be the midterm review. So we'll have the midterm review, and then the midterm will come out around that time. And you can all have fun. When I say write this giant 40,000 line C program in assembly code, get it all working. So, and you have 6 hours. So, anyway, all right. Well, I'll see you all on Monday.